Okay, welcome back to my second video on our quantitative analysis. Let me just hit play here. We'll start from this slide. So where we're going to start is we're going to look at different types of acid-base titrations. The method that we've looked at already is called a direct titration, where we just add either the acid to the base and we look for the endpoint by the change in color by the indicator. But there's a few other ways that we can do a titration that we need to look at. The first one is using a pH curve. So that's monitoring the pH as we add one to the other and finding where the maximum point of change is in pH. Another way that we can do is monitor the conductivity as we add one to another, and that will also help us to determine where the equivalence point is. And we've also got another one to learn about back titrations and redox titrations. So using titration curves. So instead of using an indicator, what you can do, you can also use an indicator too, is you can monitor the pH of your mixture in the bottom underneath the burette as you're adding one of the reactants in. So here on the diagram on the right hand side, look at the bottom, look at the x-axis, volume of acid added. So they've started off back towards the y-axis, they've started off with obviously a base down the bottom, and they've slowly added in acid as they've gone along, and they've monitored the pH. So right at 0 volume of acid added, they haven't quite got it there, but it's basically pun unintended, but it is around pH 13. And you can see it slightly drop off as they add more acid, but then there's a steep drop off. Okay, and then it levels out. So there's this really steep inflection in this curve. Okay, and we can tell with these acid-base titration curves, the steepest point in the curve is the equivalence point. So here, it's really hard to tell because it's so steep, but it's basically halfway along and it's pH 7 there for equivalence point. So wherever the curve meets where our pH is 7, and we do a dotted line down, we should see the volume of acid added there as well. So even if you're doing this, you can use an indicator in there and you'll see it happen as well. So the equivalence point is the inflection point, the steepest gradient on the plot there. Okay? So the first type that we've got though is what we've just been talking about, and it's a curve produced when you react a strong acid with a strong base. You get this very distinct, very steep titration curve. Okay, and it features a steep inflection, and its equivalence point, the steepest point, is around and pretty much pH 7. That's because the salt that is produced is neutral. Okay, so here we've got neither acid base or an excess at the equivalence point, but we've got a neutral salt because the conjugate acid and conjugate base are not strong enough to react with water. Strong base produces a very weak conjugate acid, and a strong acid produces a very weak conjugate base. Both are not reactive with water, so they won't form hydroniums or hydroxides, so that's why the salt is neutral. Okay, and as soon as you start adding in hydroxide in excess, other way around, we're adding acid, so acid in excess, it drops right down. Okay, so you get that very, very distinct sharp curve there with a strong acid and base. Now here you'll notice, I've just done the mirror image of the diagram, and what I'm trying to say is, if you change what's in the burette and what's in the conical flask below, it doesn't matter. Okay, you still get that kind of distinct shape. So if you're starting from an acid and you're adding in a base, you still get the mirror image of that curve. It's still the same shape. All right, so I've got a practical that I've filmed and I've got results for of making all these types of curves, but let's talk through them theoretically. Okay, when you've got a weak base with a strong acid, you still get this nice S-curve, but you'll notice it's less steep. Okay, you get this, so here what they've added is, well, they've started at 0 volume of acid added, so they started with our base down the bottom and they've slowly dropped in an acid that was in their burette. So as time went by, they've added more and more acid, and they got this steep kind of curve here. You can still find the equivalence point, which is the steepest part of the curve, and you'll notice here that it's below 7. We've got an acidic endpoint, we've got an acidic equivalence point here, okay? And that's because we produce an acidic salt, okay? A weak base plus a strong acid is going to produce, a weak base is going to produce a strong conjugate acid, okay? And that's why the pH is less than 7. Okay, let's look at another one. When you've got a strong base with a weak acid, your pH will start high and you'll get your equivalence point. You'll still get this kind of steep curve, but not as long as your strong, but you'll get an end point that's in the base range. And that's because your conjugate acid, or have we got this around the right way? So that's because, your conjugate base of your weak acid is quite strong, so it will react with water to form hydroxide. So that's why the pH is above 7 there for the equivalence point. But you get that curve also. Let's talk about the fourth option here, a weak with a weak. What ends up is you get a curve like this. It's a namby-pamby kind of curve that you don't really get a kind of inflection for, and it's really hard to tell where that equivalence point is. So here, looking at this curve, look at kind of the red area that I've used there. It's really hard to pinpoint exactly when that inflection is, so it's really hard to pinpoint where the equivalence point was in that range. It's quite difficult, and because you've got that amount of uncertainty, you've got a lot of uncertainty in your unknown. So because of that, the lack of steepness in the curve doesn't give kind of like a precise equivalence point. We never do weak titrations, okay? We never do weak titrations in this method at all with a pH probe or an indicator, okay? The salt produced will be around pH 7. It really depends on which is stronger than the other, but it's around 7-ish. It's quite hard to determine, and we don't have the skill in the course to do that. So we don't tend to do direct titrations with weak and weak, okay? There is a method that we can use, but we'll talk about that soon. Okay, now I need to go over, and I feel it's important to talk about endpoint versus equivalence point. Remember, the equivalence point is the point where no reactant is in excess, when there's a stoichiometrically equal amount of them, okay? And the end point of our reaction is where we see a colour change. Now, if you've got a well-designed titration, they should be roughly the same point. But if you've got a poorly designed one, they're not going to be at the same point, and you're wasting your time. Okay, let's look at an example here. So on the right here, I've got a strong acid, weak base titration curve. The equivalence point that we've got there, which is at about 81 mil there, steepest part of the curve. Now you can see that there, the colour change for both the bromothiamyl blue and the methyl orange, is that too far along? Roughly meets it there. But the thing is that if you use phenolphthalein by mistake, it's going to change colour roughly the 30 mil mark there. It's not going to, so if you use the wrong indicator, you're going to reach your colour change at 30 mil in and go, oh, there's the equivalence point, but it's not. It's too early. You need to choose the right one. Okay, let's look at a couple of other examples here. So we've got a titration curve up the top right between a strong base and a weak acid. Okay, so the equivalence point is up around pH 8 or 9. So phenolphtalene's a good indicator because it changes from pink to clear at around that point. So it's a really good indicator, it fits there. Notice that the bromothiamyl blue underneath isn't too far off as well because it's so steep. But that methyl orange endpoint is too far along the curve. We're going to get it beyond the endpoint there. So we're going to think that we have more mils of acid or base there, and it's going to be inaccurate. Okay, bottom left, we've got the classic really steep strong acid, strong base curve. Okay, so the equivalence point really matches up well with the bromothiamyl blue there. It goes from blue to yellow right at that point. But looking up there, the steepness in the curve shows that the colour change in phenolphthalein is actually quite accurate as well, because the difference in the amount of acid added between the phenolphthalein endpoint at around 9 and 7 there is not that much volume at all. It's maybe 1 drop. And then look down as well, the methyl orange endpoint, which is around 4 or 5, hits the curve at not that much more volume. So for a strong acid, strong base, it is more accurate, you could say, to use bromothiamyl blue because it matches the endpoint. But if you're in a pinch, it's not too much more inaccurate to use either the phenolphthalein or the methyl orange. Okay, couple of videos there on acid-base pH curves. Now, the other way we can do titrations is to measure the conductivity during the course of a titration, and these ones have a term. They're called conductometric titrations. Now, there's several advantages to doing conductometric titrations over other titrations, the ones that we've already learnt, direct titrations. Okay, they're very good for our analytes that are very low concentrations, so trace levels. So the direct titrations, we're looking at solutions that are about 0.1 moles per litre or 0.01 moles per litre. They're not going to deal with 1 times 10 to the negative 6 moles per litre, whereas conductivity will. Okay, they're very good for if we've got solutions that are either coloured or they've got material in there. They've got some kind of colour to the solution, or they've got some kind of stuff in there too that prevents you from seeing an indicator. Okay, and we'll do a prac soon where we're going to measure the acid in Coca-Cola, and that fits directly into this problem. Coca-Cola has food colours in there. You can't use an indicator, an acid-base indicator, and see colour change because of that brownness of it. So I chose to show you a titration, a conductivity titration to get around that, where you're not using an indicator, we're using our conductivity to find the endpoint. Okay, sometimes when you're adding an acid to a base, you can get a solid precipitate forming, and that could also obscure our indicator and stop us from seeing that endpoint. Okay, and the fourth option there is when you've got a weak acid, weak base, when you've got no other choice that you need to do a weak one, you can do it with a conductometric titration. Okay, how we do it is we need to realize that the electrical conductivity of a solution is all about, it's a function of the concentration of the ions and their mobility in the solution and the temperature of the solution. Okay, the concentration of the ions can be variable with the concentration of the species and the degree of ionization. So how much it ionizes will determine the concentration of the ions as well. So a concentrated solution will conduct more than a dilute solution, because a concentrated solution will have more ions than a dilute solution. A strong acid or base completely ionizes, so it will have more ions, so it will be more conductive. A weak acid or base will only partially ionize, so it will have lower conductivity. So conductivity will change during the course of a titration, as different ions will be present during the course of the reaction. The equivalence point can be determined by plotting the conductance versus the volume of the titrant added. Okay, so here on the right, and you'll see in a video where I filmed it, they've got a conductivity meter there, and they've got their beaker with a conductivity probe they're measuring, and I'd say they'd have a burette dropping in there. And so what you do is produce a conductance versus millimeters of something added here. So on this graph on the right, we've got a changing conductance over the amount of millimeters of strong base added. And you can see that it's a very distinct curve there. It's a very distinct V shape. Okay, So let's go into these factors that could affect the conductivity. So the concentration. So more ions will mean that more charge can move through a solution. So a solution of higher concentration of ions will have higher conductivity. So on the left, I've got high conductivity with a lot of ions. On the right, a smaller amount of ions, low conductivity. So the solution equilibria or acid-base equilibria, all those K values, will determine how many ions are produced at equilibrium. Large values will produce more ions and therefore be more conductive. So high conductivity, I've got an acid with a very high Ka value there. It's completely ionized, will have high conductivity. Whereas on the right-hand side, I've got an acid that is very weak. It's only ionized one of those three potential acids there, or only one of four, sorry, I should say. And so it has a low conductivity. Okay, the other thing that can affect it is the ion size, because it's all about the mobility, how easily these ions can move. So larger ions are less mobile in solution, so they're less conductive. Okay, so let's look at chloride. Chloride is more conductive than nitrate that I've got here on the right-hand side, because chloride is smaller, nitrate is bigger. So it means it can wiggle in between all the other molecules around and can move quicker, so therefore it's more conductive. The temperature also affects. High temperatures will give more kinetic energy. Therefore, the more kinetic energy, they'll be more mobile and more conductive. Hotter solutions will have higher conductivity than lower temperature solutions. Okay, so let's look at our first kind of titration here. We can do a strong acid with a strong base, and we get this very distinctive V-shaped curve. Okay, it starts at a maximum, and it ends with a maximum, a high value, and in between there's a low value, and it's a non-zero minimum, okay? And that's our equivalence point. So let's start doing a model of this. And notice the red line that I've got so on there, on the graph there. As we've got 0 mil of strong base, we've only got our strong acid in there. We've got a large amount of ions. So in my model here that I've got on the right, I've got 12 particles, and out of those, 83% are ions, 17% is neutral. So I've said that the relative conductance is high. As I move along to the right and I add more strong base, let's add them in. I think I've done an animation, and we can see what happens. So they're added in, my base. They react with the hydroniums. The hydroxides react with the hydroniums, and the sodium pluses go into solution there. So I've taken out some of the ions. So out of my total 18 particles now, I only have 56% ions. Okay, so the conductivity has gone down because I have less ions now. I've neutralized some of those hydroniums and turned them into water. So my relative conductance has gone down, so I'm calling it a medium. As I go along, I'm going to add in 2 more molecules of sodium hydroxide here, and they react with the last 2 hydroniums, and I've got this equivalence point. I have neither my sodium hydroxide or hydrochloric acid in excess, I only have salt and water. So out of the 22 particles, I've got 45% as an ion. I've only got the sodium pluses and the chloride minuses, so it has a relatively low conductance. But notice it's not 0 because I still have the salt left over that's soluble. Okay? Once I start adding some more strong base beyond the equivalence point, adding three more molecules, they go in, they don't react with anything. There's no acid there to react with. The hydroxides just float around and the sodiums just float around, so I'm increasing the amount of ions here. So out of the 28 particles now, 57% are ions, and so that's within our range of medium now. Okay, so that's why it increases beyond that equivalence point, because now those ions are not reacting with anything, so the number of ions are going up, so the conductance goes up. Okay, so for a strong acid, strong base, we get this distinctive V shape, and that's due because at the start we've got a lot of hydroniums, okay? And then as we're adding the base, it goes down to 0 hydroniums. So all those hydroniums react with hydroxide to form water, which is well, it's not going to add to the conductivity because it's not an ion. Okay, and so the minimum there is that equivalence point. We've got neither in excess. But as soon as we go beyond that and add in more base, they've got nothing to react with. So the base that ionizes adds to the amount of ions and increases the conductance as well. Okay, let's look at our next example. This is a graph of a strong acid with a weak base. So I've used the example of hydrochloric acid reacting with ammonia and forming ammonium chloride. We get this distinct shape with conductance. Let's take a look at our model. So at the start, I've just got my strong acid. Like before, I've added in 5 molecules of HCl and they've completely ionized and formed 5 molecules of chloride and 5 of hydroniums. So out of my 12 particles, I've got 83% that have ionized. So very high conductance there. And now I'm going to add some base in there. I'm going to add 3 ammonias into this model. Okay? They're a base, they're going to react with my acids there. Okay? Notice not all of them reacted. So out of these, because it doesn't react with, because it's got low ionization, only one of them's really reacted there. So out of my total particles now, I've got 67% are ions. So it's a medium relative conductance. Okay? Right here, to reach this point, I've got to add 2 more molecules in. And this is my minimum. Okay? And that's my equivalence point. I don't think I've done this right. Would they still react? Well, I'd have ammonium chloride left over. I've got 2 ammoniums. Well, yeah, because it's yeah. I think I've done it right. I'm happy with it. And as you go along and add more in, I'm just going to keep going. It's still going to give relatively, because it's the Kb value doesn't change, the amount that will ionize doesn't really change, it's still going to ionize in the same ratio, so it's still going to have the same conductance as you go along. That's not a good explanation. I'll work on that. So for a strong acid weak base, the shape is distinctive because the number of ions decreases because you had a lot of ions from your strong acid and it reached an equivalence point, and after that, because you've got a weak base and not all of it ionizes, the more base you add in, it doesn't change the conductance because it has the same ratio that will ionize or as you go along. So the conductivity doesn't change by the amount of base you add into there. Okay, if we take it the other way, we've got a weak acid with a strong base. We get this kind of, this is not a sharp curve, but a kind of a U-shaped curve. Okay, so our example here we've got is our ethanoic acid and our sodium hydroxide. Okay, at the start here, we've got our, well, we must have added 5 molecules of ethanoic acid, and 3 of them out of the 5 are ionized and formed ethanoates, and 3 hydroniums. Okay? So out of the 12, 50% are ions, so we're starting at a medium. Okay, let's add some base to here and see what happens. So our base is going to react with some of the acids that are there. So it's going to react with the hydroniums as well. And we're going to end up with this mixture that has now 40% ions, so a lower conductance there. Okay? And then once we add the stoichiometric ratio, the last one in there, it's going to react with the last mole of, and it's actually going to be a slight increase in conductivity because now I've got slightly more ions. There I had 40%, here I have 45%. So this is a hard endpoint to see. It's going to be an initial dip and then it's after that dip. I didn't put a relative conductance. It's still medium. It's just slightly higher. And as we add more in, more base, beyond that our conductance is going up because our strong base fully ionizes. We're adding in more hydroxides and more sodiums. So it goes up to a high after that. okay? And if I've got so for a weak acid, strong base, the curve has a distinct shape. So it starts off at a medium because we've got a weak acid, only a certain percentage of that ionizes, okay? And as we go along, that decreases because the base that we add in neutralizes. So we reach a minimum there, okay? And after that, when we're adding more sodium hydroxide, the increase in concentration is steeper because sodium hydroxide fully ionizes. Okay, so for a weak, we get this very distinct graph where we're starting low and we reach a maximum, okay? So at the beginning, I've got my weak acid, which is acetic acid again, ethanoic acid. And then I'm going to add one molecule in. So it reacts with a hydronium and it forms ammonium there. So I've got ammonium ethanoate left over in the salt there. So the conductivity actually went down a bit. So there I had 25%, now I'm at 22% with one molecule added. Now I'm going to add two more. So they react to form ammoniums and some ethanoates. And here I've got 36% ions out of the 11 total particles. So I'm forming more ions, so it's going up to it's increasing, sorry. As I add one more into there, it's at its equivalence point, okay? It's at its maximum. So 50% ions. And as I go along, I can add in more. And because of that Kb value of ammonium, the relative percentage doesn't really change because it doesn't fully ionize. So even if I go further along that curve, it still stabilizes. It reaches a point of maximum number of ions and doesn't increase anymore. So for here, the equivalent point is that start of the maxima, that first kind of top peak, and then it just goes stabilizes. So it has a distinctive shape because the weak acid and weak base, very low ionization, so low conductance. And it increases as I go along until it reaches a maximum and then it stabilizes. Okay, I've just filmed this practical. I'll put it up soon. So that's analyzing how much acid's in Coca-Cola by conductometric titration. Okay, I'll give you the info for that soon. And there's another video there. All right, you got enough to do worksheet 6.6. Okay, let's talk about back titrations. So a back titration is a titration that can be used when you can't do a direct titration. It won't give reliable results due to a couple of reasons, and we'll talk about them. So it involves adding a species, like a chemical species that will react with the analyte, and you put it in an excess amount, okay? So you're deliberately dumping a whole heap of some known in there to get rid of any possible trace of what you're trying to find out, and reacting it all away. So that thing that you added in excess will react with what you're trying to find out, and there'll be some leftover stuff that didn't. And what we then do is we do a titration of what's left over, okay? So if we know a total amount of stuff that we put in, and we do the reaction, and we know how much was left over, we can use just simple maths to find out, well, how much would have reacted? And that's the basis of a back titration. So back titrations are handy in the following situations. They're handy when the endpoint is difficult to read, okay? Especially if your reaction proceeds very slowly. If the sample is not dissolved in water, sometimes a back titration helps. If the sample is toxic, if it produces a gas, is a mixture of gases, or is also very, very small in concentration, you might want to think about doing a back titration. So here I've done a couple of models too to get your head around it. Okay, the problem that I'm basing it off is it's a reaction between limestone. Okay, we want to determine how much calcium carbonate is in the sample of rock, which we call limestone. How much calcium carbonate's there? Okay, for various reasons we can't do a direct titration. we need to do, and we've got the equation here, that the calcium carbonate is going to react with hydrochloric acid to produce the salt, calcium chloride, water and carbon dioxide, because we're starting from a carbonate. Now the trouble is that carbonates will also dissolve in water and react and form an acid. So we want to get rid of all of that. So when they do the reaction, they want to heat it and make sure that all the carbon dioxide is driven away, okay? So I've done a model to think about it here. All right, so I've got my 6 moles of acid in a beaker here, and I've got some unknown number of moles of calcium carbonate going in. I don't know how much is going in, but I know I've got 6 moles of acid there floating around, and it's a strong acid too, because it's fully ionized. I'm going to put those molecules in, and I get some number of less than acid. So I've used up some of the acid, 6 minus some number of moles of acid are left over. And look at the carbon dioxide's floating away. So I know I've got some number less than that, okay? What I'm going to do then is that number less than that, I'm going to titrate with a base, okay? And here I've got sodium hydroxide in my burette above it, and I'm going to start adding them in. And I found out that after I've done that initial reaction, it only took 2 molecules of base to react with whatever acid was left over. So if I use 2 molecules of base, there must have been left over 2 moles of acid. And because there was 2 moles of acid left over, here we go, if there was 6 moles of acid before the reaction and 2 moles left over after I had done the reaction, 4 moles of acid must have been consumed, okay, during my reaction with calcium carbonate. And if 4 moles of acid were consumed by my stoichiometry, I must have had in there 2 molecules of calcium carbonate at the start, okay? So that's how back titrations are done. You start with a known amount of what you're reacting it with. You react your unknown with it, and you get some unknown left over, okay? We had excess acid there. We've got some unknown number of acid left over. We determine how much acid was left over in a titration, a back titration. And because we know how much was left over and how much we started off with, we can calculate how much was used and therefore calculate how much unknown we had. Okay, so a couple of problems there. I'm sure I did a video where I talked through them too. There's a video here of a back titration, and the calculations also from the same producer, the same YouTube user, a calculation for it. Okay, the last type of titration that we're going to learn about is a redox titration. And if we have time, we might do an analysis of vitamin C in orange juice. So redox titrations, the difference here with these ones is that we see the equivalence point by the colour of the different species before and after, rather than an acid-base indicator. So these aren't acid-base reactions necessarily, they're redox reactions. And either we have a coloured species in the reaction, or we can add in something like potassium permanganate to show a colour change at our equivalence point. Okay, redox titrations involving coloured species of transition metals do not need an indicator, as the reactant and product are different colours. So one of the most common ones that you might see at university is the determination of iron. I think it's iron 2, so it's yellow in colour, and you use something like dichromate with it, so it's a yellow through orange titration. So here the colours of the species are their own indicator, and it's really handy with redox. So there's some 2 examples by video, and if we get time we'll do that prac. Okay, even if we don't, we've done the soft drink one earlier, and we've done some other ones like you could argue that vinegar is a common household substance, of course, and we've already done an analysis of vinegar. All right, analysis of household substances, Ed Roller. One of the last things we need to talk about is a buffer. So a buffer is a solution that resists pH change. Okay, so it resists changing pH when either hydroxides or H pluses are added to it. So there's something in there that soaks it up and stops it changing the pH. So they're either a solution of a weak acid and its conjugate base, or a weak base and its conjugate acid. So when hydroxide or hydronium is added, the equilibrium is shifted and the hydroxides and the H3 plus do not change dramatically. So basically we've got some species soaking up those H pluses or hydroxides. So a buffer solution resists a pH change. Okay, so on the diagram here, in the middle there, I've got a solution of just water. And if I add some H3O to it, the pH goes down to 4. And if I add some hydroxide, the pH goes up to 10.5. But if I have a buffer at 7, I can add some hydronium, and the pH doesn't change much at all. It just goes down to 6.9. And if I can add the same amount of hydroxide, it doesn't go up by much. It just goes up to 7.1. So a buffer resists pH change, even though you add in H pluses and hydroxides. So an example of a buffer it can be made by mixing equal amounts of ethanoic acid and sodium ethanoate. And so look at my equilibrium reaction there. I've got ethanoic acid and water and the ethanoate ion on the right, hydronium. If I put more ethanoate in them, I get what's called a buffer. Okay, ethanoic is a weak acid, and so the equilibrium lies very far to the left. Not much ethanoate is formed, but if I add more ethanoate ions, it will push it a little bit more to the left, but it will also be now a buffer. Okay, it contains a lot of unionized ethanoic acid. It also contains a lot of ethanoate ions, and it contains a very small amount of hydronium ions, and it contains a lot of water and sodium. I don't care about those though. Okay, so if I've got this mixture, if I add in H plus ions, what they're going to do is they're going to react with the strongest base there. And the strongest base is the ethanoate ion. So what it's going to do is it's going to take away the ethanoate ion and push the equilibrium to the left. But the concentration of hydronium is going to remain the same. It's not reacting with it. Okay, so it doesn't really change the pH. If I add hydroxide into this buffer system, okay, it will react with the ethanoic acid, the strongest acid. So we'll react with the ethanoic acid, and it will form ethanoate and water. Okay, these hydroxides are going to not change the concentration of hydroniums there. They're going to react with the acid and form ethanoate and water, and it's not going to change the concentration of the hydroniums. So the pH will not really change. So this buffer will maintain a pH of 4.6 until we either add so much hydroxide that all the ethanoic acid is gone, or add so much base that all the ethanoate is gone. Or have I got around the right way? Basically, if we add so much hydroxide that the acid is all gone, or we add so much, have I got that around the right way? Oh, I'm terrible. Sorry. Okay, we're going to add so much base that all the acid is gone, or we're going to add so much acid that all the conjugate base is gone. That's when it will start changing pH. Okay, I've done a little model here. Okay, a lot of water's in there. Got a couple of hydroniums, and I've got a few conjugate bases and acids in there, okay? Up the top there, I've got some acids, so some strong acid being added to it in the green. If I put one molecule in, the H plus goes and reacts with the strongest base, which is the conjugate base. So it doesn't react with water to form hydronium. Okay, so the concentration of hydronium doesn't change. So the pH doesn't change. If I keep adding them in, they react with the conjugate base. So they don't react with water. What they normally do and form hydronium, they're being mopped up by the conjugate base. So the pH doesn't change. Notice throughout that the number of hydroniums don't change at all. Okay, so as I said, the number of hydroniums do not change. So the pH does not change at all. The conjugate base mops up or buffers any H pluses added so they don't form hydronium and don't change the pH. Okay, let's change it to a strong base into our buffer solution there. What happens is a molecule goes in and our hydroxide reacts with our acid and forms the conjugate base. Our hydroxide reacts with and forms our conjugate base and water. So it doesn't shift, again, the number of hydroniums. Let's add some more in. Reacts with our acid to form the conjugate base and water. So notice that the hydroniums do not change. The base preferentially reacts with the acid rather than with the hydroniums. So the number of hydroniums do not change. So it maintains, even with a strong base added, the same pH. Okay, and there's another diagram to represent it. So you can also do it the other way around. Remember I said it's either a weak acid and its conjugate base or a weak base and its conjugate acid. So here you can look through a weak base, ammonia, and its conjugate acid, which will be ammonium, and you can look through that example there, okay? 2 videos explaining how buffers work as well. I like that top one from memory. Okay, we've got a prac to do. I might film that next term. Okay, and we can talk about the buffer region or capacity. So as I was saying before, it will only buffer it as long as there's either the weak acid or its conjugate base left. As soon as one of those runs out, the pH dramatically changes here. So in this diagram, I've got this green buffer region in the middle, and as soon as I add too much base into there, as soon as I run out of the acid, it increases dramatically. So our buffer region capacity is usually plus or minus 1 pH value. Okay, buffering is important in natural and biological systems. Okay, I'm not going to talk through this part, but we've talked about it before. I'm tired. I'm thinking I want to end the video here. Oh, I've still got a bit to talk through, don't I? Okay, I'll keep going. So an important buffer system in the environment is the carbonate buffer system. And a few of you did this example when you're doing your assessment task on equilibria. It's the carbonate system. So there's an equilibrium between the carbon dioxide gas and the carbon dioxide in the water. Carbon dioxide in water reacts with water to form carbonic acid, and that can dissociate to form the carbonate ion, and that can also dissociate to form the bicarbonate ion and the carbonate ion. Okay, and these are all in equilibrium, and if you change the concentration of something, you shift that equilibria. Okay, and so one thing that we're doing in changing this is we're adding more carbon dioxide to the atmosphere, and that's forcing the equilibria to produce more carbonic acid in our water. So it's acidifying our water. So the pH of our water is decreasing over time, and that's affecting a lot of species that produce carbonate shells. It's forcing the bicarbonate ion to increase in concentration, and therefore for there to be less carbonates to react with calcium to form shells that protect living things. So large populations of these animals that produce carbonate shells are dying and not being able to reproduce because they can't form enough protection. There's also buffers used in living things within them. So enzymes, proteins, and other long and complex biological need specific shapes to function properly. So very long molecules have specific shapes. If you change the pH of that is around these shapes, they can change them. And because their shapes are specific to the job that they do, if you change the shape, they can't do their job. So maintaining a stable pH is very important in biological systemes. Okay. Another thing is, so hemoglobin, this molecule, the heme molecule on the right, it transports oxygen through the body. Okay, if the pH of the bloodstream needs to be close to 7.4, and it's maintained that by the carbonate buffer system. Okay, and we can tell if we've had too much carbon dioxide in our bloodstream. It adjusts. It is maintained by our buffer system, but it causes us to breathe more heavily, and it's one of the signals that goes to our brain is the pH of our blood in this buffer system. It tells us when to breathe and not. When we're doing strenuous activity is when the pH gets too low, and therefore our brain says, oh, you need some more oxygen, you need less carbon dioxide, so you need to breathe out more. Okay. So some stuff. So you also need to talk about how acid-based analysis techniques are used in industries and by Aboriginal and Torres Strait Islander people. There's some notes to take from the textbook, and also how Indigenous people use acids and bases, and there's some notes in the textbook there. And we've got an Ed Rollo video and extra help, acid-base titration by Professor Dave there. All right, I think I'm all blabbed out. Hopefully that worked well. Give me some feedback, and I'll try to do that some more. That took a bit of time though.